cruise down the street and you leave chaos in your wake. As you drive or ride your bike, you've probably noticed the wind whipping around you. Here's what the airflow looks like. These disturbances in the air and other fluids are known as turbulence. Quantifying these fragmented flows is one of the greatest problems in math. If researchers can find a way to capture this chaos in an equation, we'll be better able to understand this universal event, from locomotion to ocean currents to how gases move throughout galaxies. Turbulence is everywhere if we look close enough. Blow out a candle and watch the swirling of the smoke trails. Disrupt a stream with a stick and see the little whirlpools form in the wake. On larger scales, ocean currents sweep across the globe. Storms churn the atmosphere on Earth and other planets. How can researchers study the chaotic phenomenon known as turbulence, and what's preventing them from capturing the full picture? Fluids are gases and liquids that flow and adapt to the shape of a container. Think water, honey, blood, and air. They have quantifiable properties like viscosity, velocity, pressure, and density that mathematicians can track over time. They're also governed by the laws of conservation of mass, energy, and momentum. Mathematicians describe fluid flows using the navier-stokes equations. You can think of these equations as Newton's second law for the motion of fluids. Force equals mass times acceleration. On the left side of the equation is the density and acceleration, or the change in velocity of a particle of fluid over time. On the right side is change in pressure, internal forces of stress, and finally, external forces acting on the fluid. Smooth continuous fluid flows, like in a gentle stream or pipe, are called laminar flows. The equations work well for describing how particles behave in laminar flows. But most fluids in nature are not so orderly. They can be really chaotic or turbulent. In the case of your afternoon drive, the air starts as a laminar flow as it meets the front of your car. What happens next depends on your car's shape, speed, texture, temperature, as well as the properties of the air and atmosphere. Most cars have an aerodynamic shape which minimizes the turbulence initially. As the air moves over the car, the molecules closest to your doors stay put and interact with its surface. Further away, air molecules travel at different speeds. These layers of different air create friction and turbulence, what you'd feel as drag. The result is vortices and eddies that in turn generate more and more swirls. Ever heard of the butterfly effect? It says a flap of a butterfly's wing in Japan could set up a chain of events that could trigger a tornado in Texas a week later. These eddies that beget more eddies and vortices and so on become too complicated for mathematicians to predict or quantify. Where will eddies form? How many will there be? Where will energy be concentrated or dispersed? Plug in certain values and the equations may spit out infinite values for velocity. This breaks down or blows up the model. Because of these challenges and the possibilities that understanding turbulence could lead to, there's a $1 million reward for proving either that the Navier-Stokes equations always work or that they sometimes fail, meaning velocity becomes infinite. Until then, who knows what chain of events you'll start by taking your Sunday drive.